Our group member consists of me, Maisara Ruhi Zikri, and Aina Zahira. An estimated 65 million individuals worldwide rely on wheelchair due to a diverse range of medical conditions such as spinal cord injury, cerebral palsy, and spina bifida. The solution proposed to reduce such negative effect, including various vibration absorption technique. Then, finite element analysis is a very important technique used to develop, simulate, and analyze the structural soundness of the most essential part of wheelchair, including caster and stem bolt. The structural deformations and stresses can be assessed under simulated impact load and static loading condition using this technique. This study will consider that the wheelchair front caster fork assembly as the area of concern. This is our project draft and assembly of the casters using CATIA software. For method, mainly we are using CATIA software and ANSYS software to achieve our objective. This is our flowchart of method which used to make structural analysis. The initial product assembly is made out of aluminum alloy as the basic fabrication material. So, in order to examine performance optimization and meet the demands of the comparative design stage, titanium alloy was used as the substitute high-performance material. Both material has been set up inside the ANSYS engineering data environment, taking into consideration linear isotropic elastic behavior of both of the material. As per the project requirement, at least two types of contact, bonded and frictionless, were utilized on the 19th contact area in order to ensure proper load transfer without any geometric penetration. Bonded contact were defined in mostly of the assembly joint to simulate a perfect connection where the parts cannot separate and slide due to the application of static load. On the other hand, frictionless contact interaction were created on the interface between the pivot housing and the stem bolt.
Before we dive deeper into results, let's briefly touch upon the method sections, specifically focusing on how we set up our simulation in ANSYS. First, formation, which is like dividing our physical model into many small pieces for analysis. We choose tetrahedron elements. These are great for handling the complex and irregular shape of our wheelchair forks assembly, ensuring we accurately represent all its features. We use a global mesh size of 5 mm. This size allows us to capture the stress and deformation behavior effectively without making the calculation too slow. In total, our model ends up with around 91165 nodes and 52790 elements. Next, for boundary condition, we needed to define how our assembly is held in place. We apply a fixed spot constraint on top surface of the stem bolt. Imagine this as the point where the fork attached to the main wheel of the frame. This fixed spot prevents all movement and rotation in any direction, which accurately models how the stem bolt is rigidly mounted during the actual use. For loadings, we simulated a static force. We apply a 1000 Newton force acting directly upward along the y-axis to the bottom thread surface of the outer wheel. This is the exact spot where the wheel would make the contact with the ground. We choose this because in real life, when a wheelchair supports a heavy load, there's an upward reaction force from the ground pushing back on the wheel. Let's start with our design improvement 1, where we introduce initial pocket windows into the pivot housing. The main goal here was to reduce the overall weight of the component. Looking at our result, we saw the peak stress, the equivalent von Mises stress, slightly reduced to 111.95 MPa from the original, which is 114.92 MPa. This also led to a small increase to the factor of safety to 8.3343. However, we observe a minor increase in total deformation to 0.77150 mm. This indicates that while removing the material helped distribute high stress concentration, it also made the structure a bit easier to bend at those localized points. This modification resulted in a positive 1.58% increase in total deformation compared to the original design.
To counteract this weakness, design modification 2 adjusted the pocket profile where 3 rectangle-shaped pocket has been done and the wall thickness is reduced to stabilizing the factor of safety back to 8.33, but the deformation remained high at 0.771 mm. The downside of this configuration is the shifting mechanical compliant pattern, which result in the maximum deflections reaching around 0.83638 mm and the minimum safety of factor being decreased to 6.7227. From this evident that the combination of the shape of the cutout unintentionally affect the section modulus in a certain direction, confirming that the removal of material may only cause compliance problem. Next, design improvement 3, modification of thickness stands out as the best improvement in mechanical efficiency terms. It has the lowest peak stress state of 107.35 MPa and a maximum FOS of 8.6629 and the dramatic reduction in the elastic deflection value to 0.39250 mm. From a scientific point of view, improving the thickness of the pivot housing without changing the web cross-section helped to make the internal stress line straighter. This made the design stiffer.
Next, we investigate the effect of changing material type. We took our optimized design improvement 3 and replaced the aluminium alloy with ASTM A36 steel. Our results show that the maximum von Mises stress remained the same at 107.35 MPa. This is important because for a linearly elastic materials, stress distribution is primarily determined by the geometry and how the load is applied, not the material itself. However, the total deformation further reduced to 0.38464 mm. This significant reduction, a 49.35% improvement from the original design, is due to the much higher Young modulus of ASTM A36 steel, which is 200 GPa compared to aluminium alloy 71 GPa. A higher Young modulus means the material is stiffer, resulting in less deformation under the same load. The factor of safety remained excellent at 8.6629.
Next, the introduction of thermal analysis effects in the assembly creates an effect called constrained thermal expansion. A local thermal condition, thermal loading at 50 Celsius compared to the reference temperature of 22 Celsius introduced only at the forearm of the caster. The material of the forearm expands due to the local thermal gradient, which is 28 Celsius, according to its line coefficient of thermal expansion. Since the upper surface of the stem bowl is fixed with rigid fixed support boundary condition that guarantees zero displacement along all transition and rotation degree of freedoms, the natural tendency of volume increase of the connected forearm is prevented. The structural boundary condition transforms the thermal strain directly into higher internal stress. That stress increased drastically to 228.67 MPa. This concentrated stress region is localized between the rigid clamp and the sharp notch through the expanding forearm push on the rigid boundary. and then the FOS reduced significantly down to 1.2245, the extremely close to the yield strength of the material, which is 1. This dramatic reduction in the FOS implies that the caster assembly fails because the forearm gets hot locally while simultaneously carrying both weight and external heat.
Finally, let's look at the insight from topology optimization. The main objective here was to better understand the optimal distribution of material to enhance the structural performance and manufacturability. Using this method, we identify and remove material from the areas that experience low strain energy, effectively keeping only the skeleton of the structure. We aim to retain 60% of the target material volume. The result was impressive. The peak stress was 108.99 MPa, which is 5.16% lower than the original design. The total deformation was 0.53719 mm, a 29.27 reduction, and the factor of safety remained very high at 8.5327, an increase of 5.44 compared to the original design. The analysis clearly demonstrates effective material usage and significant mass reduction without compromising the component's load carrying capacity. A lighter components translate to benefits like reduced rolling resistance for the user. To conclude our presentation, the study successfully performed a structural analysis of wheelchair front caster fork assembly using finite element analysis. We identified that the original design had areas of underutilized material, highlighting a clear potential for weight reduction. From the three distinct geometry modification we test, design improvement 3 proved to be the most effective, significantly lowering the stress and deformation while increasing the factor of safety. We further validated this optimized design through additional analysis including material type changes, thermal stress evaluation, and topology optimization. Overall, all the objectives set for this project have been successfully accomplished. For future work, we recommend conducting dynamic and fatigue analysis to understand the component's behavior under more complex real-world conditions. It will be also beneficial to examine the thermal behavior of various materials and perform physical prototype testing to experimentally verify our simulation results. That's all from us. Thank you.